Hello everyone, welcome back to the channel. Today we're doing another Leetcode problem. Today is Leetcode problem 4. This is our first hard rated problem, and this is median of two sorted arrays. Now this problem reads, given two sorted arrays nums1 and nums2 of size m and n respectively, return the median of the two sorted arrays. Now what does that mean? What is the median of an array? Well, if we are given an array of 1, 2, well, it doesn't really matter what these numbers are, but the median of this sorted array is actually, well, first there are two cases to every single one, an odd and an even case. Here we have 1, 2, 3, 4, 5, 6 items, so it's even. And in an even, we just take the middle two numbers, add them, divide them by 2, and we get 4. However, for odd cases, pretend this doesn't exist, all of a sudden our middle number is just one digit, so it becomes 3. That's all this is. Now, here we aren't given just one array, we are actually given two sorted arrays. Let's say 1, 2, and let's say 1, 3, and 4. What we can do is just sort them, or merge them, sorry. So between 1 and 1, which one is smaller? Which one will come first? 1. Now we move this. Between 1 and 3 is also 1. Move this. Now between 2 and 3 is 2. And 3 and 4. And from here, we do the same thing. Get the middle number, we have our answer. And we actually went through every single item in both arrays. And if this was of length n, and if this one was of length m, we would have O to the m plus n. Not bad, but this is what makes this problem difficult. We are actually restricted to O to the log of m plus n. So that means we can't actually merge them together anymore. When you see log of n, we are usually restricted to some sort of binary search. So how will we do this? Let's create an example really quickly. Let's make this one be 1, 2, 4, 5, and 6, and this is 1, 3, and 4. Sorry. And by convention, the first thing that we will do is let's always label the array with that is shorter as A, and the one that is longer as B. We'll just do this for convention so it's easier to work with, because we do have to pick one of them to do a binary search with, and in this case it'll be A. And you know what, let's just make this a little bit longer just to make it easier. Yeah, there you go. 1, 2, 3, 4, 5. Okay, so if we were to actually, let's just merge them really quickly just to see what the answer should be. So 1, 1, 2, 3, 4, 4, 5, 5, and 6. This is an odd case, so we could just single out a single digit of 4. Right, now, a couple of things to notice. The very important equality here that we are going to use throughout this question is actually, if we were to break this up into halves, let's say right here, the left side is always less than or equal to the right side. That makes sense because it is a sorted array. But that also holds for these two. This is actually what we are given. This is what's more important. If we were to break this up into two halves, the left side is always less than or equal to the right side. And here, the left side is always less than or equal to the right side. Yes, makes sense, right? And you'll see why that's important in a minute. Another thing that we know is we don't even need to build this array. Let's just erase it for now. We know that the answer is 4. Let's just let's just say 4. We know the total number of items in this merged array by just adding the length of B and the length of A, and in this case the total is equal to 11. Now another thing that we know is, well, when we have an array 1, 2, 3, 4, to find a median, in this case, we get these two numbers, correct? But what we do is we can actually break it up into two different halves, just like I showed you before, the left and the right. But the amount of items that go into each one is actually total divided by 2, right? So half is equal to total divided by 2, which is 11 divided by 2. Well, this is an even case here, but let's say this was a odd case. What we do actually is we just include the extra one in our right half, our right partition, right? And this half variable will keep track of how much is in the left one. So in this case, we always round down. So 11 divided by 2 will actually just be 5, correct? So I think we could just start with the binary search now. And we will always do the binary search on array A, just to keep things simple. So we have a left and a right. And remember, in binary search, we have to find a middle index, and we do that by finding the indexes, 0, 1, 2, and 3. We add left plus right and divide it by 2. And again, we round down and we get 1. So that makes our mid here. Now, essentially what we are trying to do is, you know what, maybe we should just keep this long one just so I can demonstrate what I'm trying to say. 5, 5, and 6. Remember, we said that this 4 is the middle. All we're trying to do is actually break this up into two different halves. We have a half here and a half here. Correct? Sorry. Here we said 1, 2, 3, 4. 1, 2, 3, 4, 5. Oh, yep. We made a mistake here. This should be 9, and 9 divided by 2 would be 4. And if we look here, we have 4 items in our left, just like we calculated our half to be, correct? Okay. Now, what this is saying is basically we also want to break up A and B into two different halves, where we also want to break it up into a left and a right, and a left and a right, where we can actually take these two halves and they make up this half, and we can take these two halves and they can make up this half. Now, how do we know where to split the arrays? This is where the binary search will come in. So how we do this is actually we assume that we always use the midpoint in binary search, and using this mid, we will do this. We will just, everything including mid and before it is in the left side, everything else is in the right side. But now, how do we decide where to split up B? We can do that easily because remember, we know how many should be in the half. We have 4, and right now we only have 2. So that means we need another 2 items to make up our left partition. So it has to be 2. Now, how do we know that this is correct now? Remember before when I told you about the important inequality that in a sorted array, left is always less than or equal to right. This needs to hold here. If these two make up the left half, then these two need to be less than or equal to here. Now, we know that this is less than or equal to this already because they are within a sorted array. We know that this is less than or equal to this already for the same reason, but the same must be true for these two right here. They must be less than or equal to the left side must be less than or equal to the right side, and the same goes for here. And we can do that by just checking the maximum element of the left sides and the minimum elements of the right sides. So is 3 less than or equal to 4? Yes, that is good. Now we check this. Is 2 less than or equal to 4? Yes. So that means that we split it up into the correct partitions. That is all. That is the hard part of this question. Now we will do another example where we don't get it right on the first try, and you will see how we will keep going with binary search. But from here, how we will get this answer is actually, well, remember we have an odd number of elements, and notice how we are splitting up this array. Our answer is the minimum of the right side. So our answer is actually going to be the minimum between the two different answers. In this case, they are the same, 4 and 4. So our answer would be 4, which is correct. Now, let's try a different type of arrays. Sorry. Let's try B being, let's make B high numbers, 7, 8, 9, and 10. And let's make A short numbers, 2, 3, and 4. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So our total is 10. And this is good because we have an even case, so we'll go over how to do that now. And remember, our half now is actually 5. And how do we do that? Okay, so we do the same thing. We will do a left and a right. We figure out the midpoint, which is here. Now we break it into a left and a right. And we are using 2 items in the left partition, but our half is actually equal to 5. That means we need, different color. We need 3 more items. And that leaves these to be the right. Okay, now let's check. Is 2 less than or equal to 8? Yes, so that works. Okay. Is 7 less than or equal to 3? No. It's actually incorrect. So that means that we split this up incorrectly, and we have to switch this. And what we can think of this as, well, the 3 is actually less than or equal to the 7. So that means that we want more of A to be a part of the left partition and less of B, right? So what we have to do is actually move this mid more to the right. That way our left partition will be made up of more items from our A. I hope that makes sense. And let's just quickly remove these. Remember, we said we want more of A and less of B. And let's just focus on that. More of B. More of A, sorry. How do we decide where we break up A? It's decided by this mid variable. And if we want more of A to be in the left partition, we actually have to move it to the right. So what we do is actually set our left equal to mid, and now we recalculate mid, and now it's here. And we do the exact same thing. Break it up. And now we have 3 items in our left, so we need 2 more. And all of this. Now, very quickly, let's check. 3 less than or equal to 7? Yes. 6 less than or equal to 4? No. So we're still not there. So actually, we have to do the exact same thing again. We move our left to, well, actually, okay, we did make a mistake, sorry. When we go back to here, we shouldn't be moving left to mid. We should be moving left to mid plus 1. That is how binary search should go. And from here, we can actually, let's just try that again. 3. Well, okay, we do end up with the same mid anyways. So we're here, okay? And we already checked these different points, and we said that doesn't work. So we have to recalculate. We have to move to L to mid plus 1. And see, that's why we have to do that, because if we didn't do that, then left would be stuck at mid. If we were to recalculate, it would be here now. And if we see this now, this is also an interesting case, because it appears to be that we don't have a right partition anymore in A, but we do have to compare this 5 over here with something. So, but since we are at the end, we can just assume this to be infinity. No number is bigger than this. And if it was the other way, on this end, it'd be negative infinity, which we will take care of that in the code. Now, we do this comparison again. Is 5 less than or equal to infinity? Yes, it is. So that's correct. Is 4 less than or equal to 6? Yes, that is correct. So there you go. We're done with the binary search. Now, how do we get the answer from all of this? What we do is actually, because this is an even case, and if you remember at our example here, let's say we were to add another number. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would want the middle numbers actually. We want this 4 and 4. But if we did have that, then we would actually have to redraw. We would have to redraw these partitions, because now, well, it changes. We have another number. We have, oops, what is? I don't know why it's buggy, but let's say we have a even number. We have 6. So we have a, I probably shouldn't have used blue, but it's okay. We have 3 and 3, and our two middle numbers are actually these two. And if you see, this number is the max of the left partition, and this is the min of the right partition. So if we use the same logic, we need the max between the left, which is 5 and 4, plus the min between the right, which is 6 and infinity. We divide this by 2, and we get 5 plus 6 divided by 2, which is equal to 5.5. Now, if we were to actually rebuild this array on our own and figure out the answer, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is even number, so we have to grab the middle 2, and we have the same thing. 5.5. Now the total runtime of this would end up being O to the log of n plus m, which follows the restriction they give us, meaning this method should work. So let's hop on over to Leetcode and see if we can code the answer. Okay, so now that we are actually over at Leetcode, let's see if we can write this out. If you guys are still iffy about my explanation, I would highly suggest you check out Leetcode's video on this. I'll leave a link in the description. He does a very good job at explaining this question, and I actually learned it from him first. So let's first start by assigning our A and B, and we're just going to assign them to nums1, nums2, and remember, we want A to be the shorter one. So if the length of A is actually greater than the length of B, well, we want to swap them. And we can actually do this by just returning the answer to the median sorted arrays, the same function, but instead of nums1 being first, we're actually going to reverse them like this. So this will ensure that past this point, we always have the shorter array with A. Now, what else do we need? We need a total variable, which is just the length of A, plus the length of B. We need a half variable, which is just, this is equal to the total floor division by 2. We need a left for our binary search, a right, which is just the length of A minus 1, and we need now we can start the binary search, and while true, because we will always get an answer, let's figure out, we need to find the mid of A, which in this case would be mid A is equal to L plus R, divided by 2. Now we need the mid of B, and what is the mid of B? This is just the index well, we'll treat it the exact same way we did with the mid of A. This is the index which decides where we split the partition of B. And how do we do this? Well, we get half, right? Um, well, we have half, and we already used up mid of A amount, right? Because let's say we need half is actually 4, and we already used up 2 items. We already have 2 items in A as part of our left partition. That would make mid A 1. So then half minus 1, that would be 4 minus 1 is equal to 3. But that actually means that we need 3 more items, but the index to 3 is 2. I think I might be overcomplicating it. Let's just let's say A is 1, 2, 3, 4, 5, and B is 1, 4, 5 is 2. Oops, they have to be sorted. 5, 8, and 9. So that makes half equal to 5. Sorry. And our mid A would actually be this variable right here, right? So this would be 0 plus 1, 2, 3, 0 plus 1, 2, 3, 4 divided by 2, which is the index of 2. So this 3 would actually become our middle point. So mid A is actually equal to, we said 2, right? So everything from this point on would be part of our left partition, but our half is actually 5. So we need 2 more items. So our mid B would be equal to half, which is 5, minus mid A, which is 2. And we said we want, and this actually gives us 3, but we said we want how many items? We said we needed, well, we needed 2 more items, right? And the index for 2 is 1. So we actually need to subtract another 2. So we just subtract it here. That's all that is. Now, from here, we can continue. Now, let's define a couple of variables. Let's define the left A, and this would actually be, so think about where the middle point of A is. We're just defining the maximum point of the left partition, basically. And that is just the value of A at mid A. But we have to see if mid A actually exists. It has to be greater than or equal to 0. And if it isn't, well, this is a left partition, so it has to be negative infinity. Negative infinity. Now we do right of A, and this is the left side of the right partition. So this would actually be the min point of the right partition. And again, we have to, that would be mid A plus 1. And we have to see if mid A plus 1 is less than the length of A. From here, if that doesn't exist, then we need some number to indicate that this is a maximum. And since no number is bigger than infinity, we can just use that. Now we could do the exact same thing with left B. So that's equal to B at mid B if mid B is greater than or equal to 0, else we want to float negative infinity, and then right to B is equal to B at mid B if mid B plus 1 is less than length of B. Otherwise, we want it to be float infinity. So this handles, these else statements handle all of our edge cases, because just in case that we do split the arrays in a way where either the left or the right partition actually doesn't have anything, so we do need something for us to be able to compare, which we will be doing next. So At this point, we have split it up. We have set a mid B and a mid A, and we have to do the comparison. And remember, we do that by, we have to check left B, which is, this is a minimum function, and it has to be less than or equal to right A. And this has to be true, and so does left A has to be less than or equal to right B. Remember, this is us checking the inequality across the two arrays. And if that is true, this means that we've actually found our solution. And what we have to do here is check if the remainder of total divided by 2 is equal to 0. This makes it an even case. What we have to do here is return, remember, the max of the left partitions plus the min of the right partitions. All of that, of course, divided by 2. Else, this is an odd case. Now, what do we have to do? We have to return the min of the right partitions, because remember, if it's an odd case, then the extra item always goes in the right partition. Now, let's say that it's not true. Well, we have to see which one of these was false. Let's say, what if left of A was actually greater than right of B? That just means that we have to move our right to mid A minus 1, because that means that we have too many items in our left partition in A, and we have to move the mid back. So how we do that is we move our right pointer back, so that when we recalculate our mid A, it'll actually be placed further back in the array. And we have the last case, and this would be if the left of B is greater than right of A, but it's the only possible case, and that's the one that we looked at in our examples. And if we double check everything, that should be everything. And we actually made a mistake here. This should be plus 1, because we want it to be to the right of mid, not exactly where left of B is. And if we try running it now, we should be all good to go. There you go. We get a very efficient time. So thank you guys for watching. I hope you guys find this video helpful, and I'll see you guys next video.